by the addition of salt or acid or even alkali. Okay, and if you pass electricity through it, that will be further enhanced, right? So you understood this. So whenever we have a solution, this is what we have. We have these two ions from the water molecules, hydrogen ions and hydroxide ions. And then if we have an ionic salt, ionic compound, salt, then we have the metal cation, M is for metal, any metal cation, and the non-metal anion, right? Remember, the competition is amongst them. These, the anions will go for the anode, which is positively charged because of the electrostatic attraction. The cations will go for the cathode, which is negatively charged electrode. Okay, I will come to that in a bit. But remember, there is competition between the similarly charged ions. There will be competition between these anions. There will be competition between these cations, like which will be discharged. Now, I shouldn't say competition, because competition is something that you compete for, right? I shouldn't be using the word competition. It's more like they don't want to be discharged. Why don't they want to be discharged? Okay, we'll come to that. But remember, only one type of ion gets discharged at an electrode at a time. This is written in your book, that only one type of ion is discharged at a time. Okay. Now, how does the competition take place? Now, let me. Okay. For example, let me take the example of concentrated sodium chloride solution. Okay, concentrated sodium chloride solution. Okay. Now this is solution, so this plus water, right? Sodium chloride plus water. Now what are the cations? What are the cations? Sodium ions. From here, hydrogen ions. These will compete. Here, chloride ions and hydroxide ions. And so these will compete. Compete meaning, you know, okay, so I will write down two of these ions here, two of these here, right, and then I have hydrogen ions. Now, why did they become ions at the first place? You have to remember that. Why did they become ions at the first place? To get stability, right? Because they were stable. They are stable in the ionic form. Remember, how many electrons does sodium have in its outermost shell? 1. But it tries to be like the noble gas. I mean, the inert, you know, the group 0 or the group 8 elements, and so it does not want to have any, either 8 or nothing. Okay, and when it has nothing, then the second last shell is becomes its last shell, which has 8 electrons. It wants 8 electrons in its outermost shell, because of which it lost the electron at the first place. So it is stable in this form. Now it doesn't want to lose that stability. It doesn't want to lose that stability by accepting electrons here. Okay, by the way, I have already mentioned this in the electrolysis of molten compounds, but let me repeat myself again. The electrode which is connected to the negative terminal of the battery has an excess of electrons, right? Because the negative terminal of the battery has electrons coming out of it, and those electrons give an excess of electrons to this electrode, and therefore this gets a net negative charge. Whereas the opposite happens to the anode, because the electrons are traveling towards the positive terminal of the battery, so this has a net positive charge. So it has you know, loss of electrons, right? So this is positively charged. Okay, so these cations will not get unstable by accepting electron. So because if you remember the reactivity series, sodium is high up in the reactivity series, and it won't go and become unstable. Okay, it will push this hydrogen ion that you go, You go ahead and you get unstable. I'm not gonna do it, okay? So this poor hydrogen ion will have to be sacrificed, and it will go and it will accept an electron and turn into hydrogen atom. Hydrogen atom. Okay, let me show this to you in this form. This is better. I made these for you guys. These are sodium ions, chloride. Okay, what other ions do I have? Hydrogen ions, and then what other? Hydroxide. So hydroxide and hydrogen ions from water, sodium and chloride from sodium chloride. Right. Now, sodium will accept, oh sorry, I'm so sorry. Sodium will not accept because it's the boss, right? It will push the hydrogen ion forward that you go, you get unstable by accepting electron. I'm not gonna do that. Okay, so it's the boss, okay? So hydrogen ion has to accept this electron. I made this little tiny electron for you guys, just, you know, so that you can visualize. So it is accepting this electron very, you know, unwillingly. It doesn't want to, but it has to because it is being forced, because that will make it unstable. That's why, Hala, it won't accept electron because that would make it unstable. Why did it become an ion at the first place? To get stability. Now it doesn't want to lose that stability. It is better off in the ion, in the form, in the solution in the form of an ion, because this is more stable. That's why. Okay. Does hydrogen exist as atom? No way. No. Either it will exist as hydrogen ion, or if it has to accept electron and it has to become a hydrogen atom, then what it does is two hydrogen atoms make a covalent bond and become hydrogen molecule. Okay, you know, you have also accepted electron, I have also accepted electron. Okay, let's become friends together. We'll make each other stable. Okay, we'll make each other stable. Okay, so diatomic molecule. Yes, hydrogen is one of the diatomic molecules. It does not exist as a single atom. And so this hydrogen gas will be released at the cathode, right? Cathode, because it is connected to the negative terminal of the battery. It's negatively charged. So we will have hydrogen gas here near the cathode. Okay, hydrogen gas here collected. Right, now, what about the anode? What about the anode now? Anode, opposite thing is going on. Now these, again, these are the ions. Now they're deciding who will go. Who will go? Now with the halogens, there's this thing that these halogens will be released only if they are really, really concentrated. If they are concentrated, only then the hydroxide, you know, is enough. I mean, it pushes it. And, you know, because there are so many that they cannot help, but they have to give off their electron. You know, the one electron that they gain for the sake of stability, they had to lose it. Now they have to lose it. Now, when they lose it, now what happens again? When the chloride, this electron loses chloride, it is lost to the anode. Where is it lost? The electron is not lost to the solution. The electron is lost to the anode, positively charged. So electron, when there is an excess of electrons, lots and lots of electrons, can you see? I made these so that you can visualize what's happening. Okay. So lots and lots of electrons, they travel up and they go towards the positive terminal of the battery, and so they complete a circuit. Okay. So again, now again, the same story with chlorine. Oh, they had to be unstable. They don't like it, but it's okay. You know, you have the same story as me. Let's be friends together. You are also unstable. I'm also unstable. Let's join hands together and we will become stable. It's okay if we're discharged. So what? We are still stable. So, so this is a diatomic molecule. Okay. They found some way out to be happy. Okay. So they are stable. They are good here. So Blue-green gas, chlorine, diatomic molecule. Yellow-green gas, chlorine. And this is a colorless gas, but it will give a pop sound with a lighted splinter, right? Remember the identification gases, because of course the molecules will not be like this with Cl written on them and hydrogen H written on them. You will have to carry out the identification tests in order to find out what gas this is. Now, what is left behind? What is left behind? Which ions are left behind? Sodium and hydroxide are left behind, right? So we have sodium hydroxide left behind, which is an alkali, right? Right. Okay. Okay. Can anybody name, first of all, can anybody ask me, sorry, can anybody tell me, are all the cations metals? Are all the cations metals? No. Okay. Can you name a few non-metal cations? Can you name non-metal cations? Yes, Osman, मैं atoms की दोस्ती करवा रही हूँ. Yes, वो लोग दोस्ती करते हैं. Because you know, like जिंदगी गुजारनी है तो दोस्ती तो करनी पड़ेगी ना. बगैर दोस्ती की जिंदगी नहीं चलती. Hydrogen ions. Yes, yes. Good job, Amana. But you should write ions with it, not just hydrogen. Write down H and then plus. H and then plus. That I would like it. Not semi-metals, beta Ibrahim. No, no, no. No. Yes, Amana. This is better. Hydrogen ion. Yes. And is that it? Any other cation that is a non-metal? No, 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 no. Carbon, no way. Can you think of any non-metal cation? Amna, you should know. You should know. I have told you guys. No, Arham, lithium is a metal. I'm saying non-metal. Lithium is a metal. Okay. I'm telling you, it's ammonium. Yes. Good job, Amana. Yes. See, I told you, you should be knowing this because I have told you. Yes, ammonium ion. Ammonium ion and hydrogen ion are the only non-metal cations. I won't say only, but yes, in the ordinary chemistry that we come across in O levels and A levels, they are the non-metal cations that we will be dealing with. Okay. Now, another thing, I had these mnemonics. Well, by the way, I think you can get mnemonics even from Google, but let me share. These are the two mnemonics that help me out. But another thing, before you resort to mnemonics, remember one thing. You should know the logic behind them. And then after you have understood the logic behind them, only then you should be using them just for your, you know, short, immediate remembrance when you are solving MCQs during examinations. So those mnemonics are only for that time. But don't rely on these mnemonics completely. You should know the logic behind them. Okay. So this is one I find this, you know, helpful. Tank, anode is positive, cathode is negative. Okay. Why? Another thing, cathode is attached to the negative terminal of the battery. Cathode is attached to the negative terminal of the battery, and therefore it has excess of electrons, and therefore cations, because they are positively charged, they're attracted towards the oppositely charged electrode, and so they accept electrons. So this is reduction. This is reduction. Okay. In anode, there is positive charge, net positive charge, which attracts the anions towards them, which lose electrons to this anode, to this positively charged electrode, and so they get oxidized because they lost electrons, because oxidation is the loss of electrons. Another mnemonic that I found helpful is this oiler. You know, remember that oil rig? So oxidation is the loss of electrons, which occurs at anode. So then reduction is left with cathode. So that will be easy. So if you remember just this, then you know that if oxidation is at anode, then reduction must be at the cathode. So that's that. Okay, now this electrolysis that I showed you, now I want to do half reaction. How will you write a half reaction of concentrated sodium chloride solution? Now, there are a couple of things that you need to remember when you write down half reactions. Half reactions of electrolysis of concentrated sodium chloride solution. Now, we remember this electrolysis that I just showed you. There were, which cation was getting attracted towards the cathode? Was it the hydrogen or the sodium? It was hydrogen, right? Sodium is a very bossy metal. It is never gonna be sacrificed. It is not at all patient. So hydrogen ion. So we should know which ion, right? After we have decided which ion, of course, we are starting with the ion, right? So we will start with the ion. It is in a solution, so aqueous state. Now we know that this is cathode, so must be reduction, right? So if reduction, that means gain of electrons to form the atom, right? Must be gain of electrons to form the atom. Now we know hydrogen is one of the diatomic molecules. It does not exist as a single atom. It exists as a diatomic molecule, right? Now, if there are two hydrogen atoms here, you want to chemically balance this equation. You want two hydrogen ions from here. So two hydrogen ions from here. Now, each hydrogen ion will accept an electron, right? Each hydrogen ion will accept an electron this way. Like these are hydrogen ions. Each one accepted an electron. One hydrogen ion accepting electron, becoming a hydrogen atom. Becoming a hydrogen atom. This hydrogen ion also accepted an electron and turned into a hydrogen atom. And so the two hydrogen atoms combine together to form the hydrogen molecule. Okay, I made this so that you visualize what's happening, right? And so remember, how many electrons did we use? Can you see? I used 2 electrons. I used 2 electrons, okay? So 2 electrons. Now this is chemically balanced, 2 hydrogen atoms here, 2 hydrogen ions here, and +2, -2, 0. So 0 here, 0, this is 0, and this is 0. So electrically and chemically, this is balanced now. Okay, now come to the anode reaction. Anode reaction, easy. We starting, which ion was sacrificed here? This was chloride, right? We started with chloride in the ionic solution. So this is aqueous, okay? And this got discharged as, I mean, of course, this is anode, so oxidation. Because anode is the site for oxidation. There is loss of electrons. So I know some electrons are lost. Okay, I will figure out how many later. But I know that chlorine cannot be discharged as single atoms. It has to be diatomic molecule. Right, now if I want to balance this, 2 atoms from 2 ions, definitely. So 2 minus. Now each chloride must have released 1 electron, right? Now again, I'm trying to show you this chloride released this electron and turned into chlorine atom. This chloride lost this electron and turned into an atom. And so we have chlorine atom with 2 electrons. Chlorine atom with 2 electrons, okay? So minus T, chlorine molecule. So chloride, 2 chloride ions giving me chlorine molecule and 2 electrons. Right, Now this is electrically balanced, -2 here, -2 here. Basically the charges should be equal on both the sides. Okay, balancing means the charge, the net charge should be equal on both sides of the arrow, right? And also chemically balanced. Now 2 electrons are gained here, 2 electrons should be actions, remember? Yes. So this 2 electrons cancelled. Now I will write them together. So 2 hydrogen ions aqueous, 2 chloride ions aqueous, giving me hydrogen gas, chlorine gas, and that's it. Okay, so this is the overall reaction for electrolysis of concentrated sodium chloride solution. And can you see that this is hydrochloric acid decomposing into its components, into hydrogen and chlorine. So if you write, like an MCQ, you don't have the time for all these steps. Just write down the compound, HCl aqueous into its components, and you have to know what those components exist as. So just write down their components. They're made up of hydrogen and chlorine, and they are diatomic molecules. Go ahead and balance them. This is your overall equation direct. You should know what you started with. You should know the simple components they will break down in. Write down the form in which they exist. Balance it. You will get the overall reaction. Okay? Now, if this sodium chloride solution is dilute, then how does the story change? How does the story change if it is dilute? Now, if it is dilute, the story is almost the same, except for a little change in the anions. Cation will be the same, of course. Here, the ions in competition, or the ions in question rather, are the same, which are sodium ions and hydrogen ions. Sodium ions, hydrogen ions, and then chloride and hydroxide, right? These are my ions which are in question. Okay, now the question is, which one will be discharged? Which is the bechara one? Which bechara will be discharged? Okay, these are hydrogen ions. Okay, sodium is a boss all time, so no way, no question. Okay, you keep sitting here. Okay, this hydrogen ion will go ahead. This has abundance of electrons sitting on it. Excess of electrons, negative terminal, positive terminal. Okay, this is positively charged. So where are my electrons? Here. Okay, so hydrogen ion will come and will accept an electron and turn into a neutral atom, unstable. Oh. Now this, another hydrogen ion will accept an electron unwillingly, na chahte hue, so unstable, and then a hydrogen and hydrogen, again, hydrogen is released, same story. Okay, now the anions, now here they're dilute. So let's suppose there are not enough chloride ions. Okay, there is not enough chloride ions. So though oxygen, how should I put this? So because there are not enough chloride ions, therefore it is the oxygen that will go. Okay, this hydroxide will come here, will lose its electrons. This will lose its electrons to this positively charged anode. Okay, and in the process, what will be released here at the anode? Oxygen and, oh, I don't have water molecules. Okay, oxygen and water molecules. But water will stay in the electrolyte. It will not be discharged as such. Water will stay within the electrolyte. So what are we left behind with is sodium and chloride. Okay, along with water. There will be water produced as well. There will be water molecules. Remember our Mickey Mouse, my favorite Mickey Mouse. So yeah, water molecules along with sodium and chloride will be left behind. So we have a salt solution with oxygen and hydrogen gas released at the electrode. So did you see that instead of chlorine, we got oxygen at the anode? That's the difference between the electrolysis of concentrated and dilute sodium chloride. Now, how did we get this oxygen? We'll talk that in a bit. And okay, is that it? Yeah, okay. Let's move on to the half reactions. Okay, yeah. What is the identification test for oxygen? Yeah, the lighted splinter reglows. Yeah, relights or reglows. Right. Okay, now let's move on to the half reactions. Again, the cathode reaction is the same. Hydrogen ions we know exist as diatomic, so we balanced it. 2 electrons are lost by each hydrogen ion. Same story, right? Anode reaction. Now for understanding anode reaction, I drew this. Okay, I drew this, okay? This is hydroxide. These are, okay, first let me write down the equation. Okay, write down the equation for you, and then I will show you what actually happened. Hydroxide ions, we know, gave oxygen, okay? But when I wrote oxygen, I know there are hydrogen as well. Hydrogen atom is also sitting here. What about this hydrogen? What should I do with this hydrogen? Now I should have a product which should not affect my, it should not introduce any new substance here. So I can easily say water, because water has hydrogen and oxygen, and it can get oxygen from here. So I wrote down water here, okay? Now there are 3 oxygen atoms and 2 hydrogen atoms here. So if I put in 2 here next to water, I have an even number of hydrogen and oxygen atoms. 4 hydrogen atoms and 4 oxygen atoms. 4 hydrogen atoms and 4 oxygen atoms if I add 2 here. So I wrote down 4 here, and that will easily give me 4 oxygen atoms and 4 hydrogen atoms, okay? Now each hydroxide will lose 1 electron. So that will give me 4 electrons. Okay, this will balance this equation chemically as well as electrically. -4 here, -4 here. Okay. Yep. Oh, this I got wrong. Oh, so sorry. This should be here. Gain of electrons. Yeah, sorry about this. This is gain of electron. This is reduction. At cathode, we have reduction. Okay, and this is oxidation. Okay, now I want to explain you what happened here. Now we had 4 hydroxide, okay? 2 of these oxides, O2 minus, they lost 2 electrons each. Each one gave 2 electrons. This gave away, it had 2 minus, right? It had 2 extra electrons. It gave away 2 electrons. This gave away 2 electrons because it had 2 minus. So it gave away 2 electrons, and they combined together, formed a covalent bond, formed an oxygen gas, diatomic gas. Now what are we left behind? Because they have made covalent bonds with each other, they have lost 2 electrons. So I am canceling them out so that you can visualize what is left behind. What is left behind? Can you see these 2 hydroxides are left behind along with these 2 hydrogen ions? Hydroxide with this 1 hydrogen ion. So this hydrogen ion and attaches itself here. This hydrogen ion comes and attaches itself here. This hydrogen ion comes and attaches itself here. Here. So they become 2 water molecules. Okay, can you see? These are 2 water molecules. These are 2 water molecules. So this is how from 4 hydroxides we got oxygen and 2 water molecules. Okay, and in the process, 2 electrons from each oxide, from each oxygen. So total of 4 electrons. Okay, so this is what happened in oxidation. Now, if I want to write down an overall reaction, okay, this is so messy. This is so messy. Can I write down somewhere else? Okay, okay. Now there are 4 electrons here and 2 electrons here. Okay, if I multiply this whole thing by 2, I will get, because for balancing, remember, the electrons gained should be equal to the electrons lost. In a redox reaction, the electrons gained should be equal to the electrons lost. So these are 2 and here I have 4. So I multiply this by 2. Okay, so now I have 4 hydrogen ions, 4 electrons, giving me 2 hydrogen molecules. Okay, now this and this. So 4 electrons and 4 electrons cancelled here. What do I have? 4 hydrogen ions and 4 hydroxide. Now 4 hydrogen ions and 4 hydroxides will not stay separate as such. What will they do? They will combine together to form water molecules, right? They will form together water molecules. This is getting so messy. Okay. Can you hold this? Let me use this. Okay, let me use this. Where was I? Yeah, okay. So 4 hydrogen ions, 4 hydroxide ions, 2 hydrogen plus oxygen plus 2 water. Okay. They will not exist separate. Okay. They will form 4 water molecules. Oh no. Okay. So sorry. Yes. 4 water molecules over here. 2 over. 2 water molecules only. Yes. Okay, where am I going wrong here? Okay, is this fine? Hydroxide and hydrogen. Yeah, 4 water molecules. Yes, I'm right. 4 water molecules. Yes, 4 water molecules. 2 hydrogen plus oxygen plus 2 water molecule. Now I told you whatever is common on both sides of the arrow will get cancelled. So 2 water molecules are common both. So I will subtract 2 water molecules from both the sides and I will get 2 water molecules giving me 2 moles of hydrogen and 1 mole of oxygen. Yeah, and this is that. Okay. So this is my overall reaction. So did you see? I write down the substance that I'm electrolyzing, you know, the shortcut for writing the overall reaction. Shortcut for writing the overall reaction. So I write down the formula for what I'm electrolyzing. I break it down to its components made up of hydrogen and oxygen. Both are diatomic molecules. I will write down their formulae and then I will accordingly balance the equation. So this will be my overall reaction for the electrolysis of water. Sorry. Yeah, electrolysis of, yeah, you can call it an electrolysis of, by the way, this was electrolysis of dilute NaCl. Okay, but the overall reaction for water is also the same. But yeah, this was dilute NaCl. But yes, in NaCl, so basically, I'm sorry, here the substance we were electrolyzing was dilute NaCl. So we did not start with that, but basically the water got decomposed, okay, into hydrogen and oxygen. Okay, okay. Do you have any questions? Please do not write unnecessary. I'm sorry, Atika, I was holding it and I was writing at the same time. Balance electrically, meaning that the charges on both sides of the equation, on both sides of the arrow should be the same. Right? Right. Usman Aslam, can you please kindly refrain from writing unnecessary comments, okay? When elements lose electron, do they become atom or ion? Yusra, it depends upon what they started with. If they are atom and they lost an electron, they will turn into an ion, right? And if it was an ion, right, it already had an extra electron and it lost that extra electron, it will turn into, or it will be oxidized to its atom, right? So you have to see what you are dealing with, right? Right. 2 chloride gives, okay, and oil. Yes, okay, Amana, good job. Okay. Any question? Any question? I can see hands raised. Do you guys want to ask questions? I'm sorry about the cell phone moving. Sorry. Yes, Amana, I've unmuted you.
No, I don't have any question.
No, I don't
Yes.
have any question.
I don't have any question.
Oh, your hand was raised. Sorry. Okay, Nabil, do you want to ask something? Yes. Yes, Nabil.
Yes, on page 95, there in the synthesis and decomposition 4.3, there is an exception written, but they have not mentioned the word exception. So I have to know that it is a like photosynthesis reaction. Is this synthesis a reaction or an exception of that?
Beta Nabil, we are not on page 95 right now. We are not on page 95 right now. I am doing electrolysis of solutions with you. Please ask me questions regarding what we are discussing, okay? Otherwise, we will be deviating away from our topic, okay? I have to finish one topic in a class, okay? So I will not discuss photosynthesis right now, okay? Okay, so that was dilute sodium chloride, okay? Then electrolysis of concentrated hydrochloric acid. Now, electrolysis of concentrated hydrochloric acid. Can anybody tell me the, just simply write down, okay? My cameraman will do the job, otherwise, you know, I cannot write and hold the camera at the same time. So ions, the cations are hydrogen ions from hydrogen chloride as well as from water also. From water, because this is solution, right? So this is HCl plus water. The other substance we're dealing with is water, right? So hydrogen ions from both are giving hydrogen ions as cations. The other, chloride and hydroxide. Okay, so of course, this goes without thinking that it is hydrogen ions which will be attracted towards the, hydrogen ions will be attracted towards these electrons, and they will gain these electrons, and therefore they will be reduced to hydrogen gas. Same thing, okay? I'm not repeating it. Again, here, because they're concentrated, the chloride will be oxidized to chlorine molecule, not hydroxide. It will be chloride that will be oxidized to chlorine molecule. So you will have hydrogen gas and chlorine gas discharged here in concentrated hydrochloric acid electrolysis. Then electrolysis of dilute hydrochloric acid. The only difference would be cations again are the same, hydrogen from water, and from hydrochloric acid we have hydrogen. So hydrogen will be released at the cathode, and chloride and then hydroxide. So because this is 2 less, it will be this that will have to be sacrificed this time. So we will have oxygen, okay? And the byproduct is water, which will stay here in the electrolyte, okay? So we have oxygen glowing the lighted splinter, and hydrogen giving a pop sound with the lighted splinter, okay? You should know the identification tests for these gases. Now, electrolysis of acidified water. Now, this is nothing, just electrolysis of water, but we have acidified it. Why? so that, because pure water molecule will not conduct electricity and the molecules will not split into their ions. Therefore, in order to help the water molecules split into hydrogen and hydroxide, as I showed you here, we add dilute sulfuric acid. But remember, dilute sulfuric acid. Now, we want to facilitate the conduction of electricity through water. We want to facilitate acidified, meaning that I have added dilute acid into it. Okay, that is what I mean by acidified. So those ions, hydrogen ions, and if I'm using sulfuric acid, then, and you know, basically we use dilute sulfuric acid to acidify water if we want water electrolysis. Why? Because sulfate, okay, I'll explain you. Because we want the product. Now, water is this. It will break down into its components, hydrogen and oxygen. Now, if I balance it, what will I get? Hydrogen and oxygen, and the ratio is 2:1. That's the ratio. 2 moles of water reacting with 2 moles of hydrogen and 1 mole, and sorry, splitting up into 2 moles of hydrogen gas and 1 mole of oxygen gas, right? I want this product. So I want to ionize this, but I do not want any other product. Like if I add hydrochloric acid, I have to keep it dilute because I don't want chlorine getting discharged instead of oxygen. So if I'm acidifying water, make sure you acidify it in such a way that your products stay hydrogen and oxygen. I can use sulfuric acid. Now, sulfuric acid will give me hydrogen ions. Sulfuric acid will give me hydrogen ions and sulfate ions, right? Will give me hydrogen ions and sulfate ions. So hydrogen ion is okay because that will also contribute towards the hydrogen gas. Sulfate stays in solution. It will never be sacrificed. Again, this is bossy. So oxygen will have to be discharged. So this is not affecting my product. I can safely use a dilute sulfuric acid to acidify the water to help the water molecules split so that the electrolyte can conduct electricity and my circuit can be complete. Because if my circuit is not complete, the current will not flow and electrolysis will not take place. Remember, when current behaves like water. Current behaves like water. If you block the passage of water in a pipe, for example, the water will stop flowing. Even from the tap, you have blocked, for example, a pipe is connected to a tap, okay, and you have blocked the pipe with your hand. Even the water from the tap will stop, meaning the water will stop moving, okay? All the water molecules will stop wherever they are in their respective positions. Same is the case with current. If this circuit is not complete, if there is any blockade anywhere along the circuit, okay, if I switch open the switch, the electrons will halt wherever they are. They will stop moving. And when they stop moving, they stop exhibiting their chemical characteristics, whatever they are. So, you know, the whole thing stops, okay? So, okay, hydrogen ions, and then I have hydroxide ions. Simple as that, okay? Hydrogen ions, and I am not taking into consideration sulfate ions because they will stay in solution. They will not contribute towards the products. So I have hydrogen ions and I have hydroxide ions. So the cathode and the anode reactions will be the same as I discussed before. The one that I discussed before, here, these, the messy one. This is the electrolysis of water, meaning same thing. Hydrogen ions will gain electrons, hydrogen gas and hydroxide will lose electrons to give oxygen. And when you write the combined overall reaction, what you will get is a water molecule splitting into oxygen and hydrogen. The overall reaction would be, you know what I mean, right? Water giving hydrogen and oxygen. So yeah, 2:1. Okay. Now, once we have discussed all these electrolysis and their half reactions and everything, now let's discuss this Hofmann voltameter. Hofmann voltameter is an apparatus, and now I'm sharing my screen. Hofmann voltameter is that apparatus. Basically, it is electrolysis of acidified water. Okay, it is electrolysis of acidified water, and we are getting the products hydrogen and oxygen gas. But this apparatus is designed in such a way that hydrogen and oxygen gas are not allowed to mix with each other. They're not allowed to mix with each other. So they have been separated so that we can get them, and we can use them for various purposes. Okay, that's all about this apparatus. The basic phenomenon is the same as I just explained you, that electrolysis. Okay, nothing special about this. And yes, another thing, we are using platinum as the anode and cathode. Why? Because again, platinum is stable and it does not react with the components, with the electrolyte that we are using. Okay, so because of that, we are using platinum as our anode and cathode. Then we will discuss the industrial electrolysis of concentrated sodium chloride. Now, I discussed the concentrated sodium chloride electrolysis with you, right? The same phenomenon is working in here, but they have given it a special design. They have given it this special apparatus. Why? So that the products can be separated. They are not allowed to react with each other, and we can collect each products separately, safely. This is more economical. Okay, even the sodium hydroxide, which is left behind, I just discussed the electrolysis with you. Hydrogen gas is released at the cathode, chlorine gas is released at the anode, and sodium hydroxide, which is an alkaline solution, is left behind. So you can see there's a tap at the bottom for the drainage of sodium hydroxide. Now there's this membrane, this is called ion exchange membrane between the two electrodes, and the reason why it is called ion exchange membrane is because it only allows the sodium ions and the water molecules to pass through it. Hydroxide and chloride are not allowed to pass into the other compartment, right? And the electrodes they have used is titanium, because titanium will not react with the chlorine. Okay, by the way, titanium is used for anode. Why? Because titanium would not react with chlorine, because chlorine is the product released at the anode, whereas cathode is made of nickel. I don't know why they have used nickel. Maybe because nickel doesn't react with hydrogen. I have no idea. I don't know why they have used nickel. I tried to search on it, but I couldn't find the answer. If you guys want to try that out, find out why is nickel used as a cathode. Okay, and what else? That's that. Okay, if you have any question, ask me. We will discuss electroplating and the purification of copper in the next class. Okay, you have any question, ask me. Otherwise, then we will proceed on to the questions of the book. Okay, brine is yes, concentrated sodium chloride. What do you mean by acidified? Acidified meaning I added a little acid, dilute acid, just to help the water molecules be broken into its cations and anions, right? Okay, my kids are my cameraman, Ibrahim, my kids. Okay, now any question? Ask me questions, or we will move on to the questions on page 112. Okay, Nabil, yes?
Yes, for zinc, is galvanization required in electrolysis?
Zinc galvanization? Beta, I have not talked about zinc galvanization. Please concentrate on what I'm teaching, okay? And then ask me questions if you do not understand, okay? Otherwise, you know, अल्लाह का इल्म तो बहुत बड़ा समंदर है. अब अगर हम हर चीज को फॉलो नहीं कर सकेंगे हर चीज को, तो in 1 hour we have to focus ourselves on one particular topic. Okay. Question number 4.11 on page 112. Page 112. Okay. An experiment was carried out to investigate the effect of electricity on molten lead to bromide. We have done this already, molten lead bromide. What happens to a compound during electrolysis? Yes, very good job, Hiba. Yes, it is decomposed. It is splits into its elements, which will be what? In this case, give me their formula in the chat window. It splits into its elements. Can you give me in what form? Yes, no, 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 no. No, 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 not ions, Hala. No, 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 no. Yes, Ajwa, you are right. It breaks into lead and bromine, but give me the formula. Give me the overall reaction. Who is going to give me the overall reaction for this? Molten hai, molten, molten. So no water molecules. Okay. You want to try or should I give away the answer? Yes, Saad Aslam. Yes. Lead and bromine diatomic gas. Right. Okay. So how do I get this? I will write lead bromide. Okay, this way. Lead oxidation status 2, right? Yeah, okay. So lead exists as metal atom. Metals exist as atoms on their own. And then bromine is diatomic. So simple. Bromine is gas, vapors at room temperature. Lead is solid. This is molten. Yes, in our case, it is molten. So simple. Did you see? This is simple overall reaction. Then you can, you know, reactions and so on. Let's move on. Next question. Why does solid lead to bromide not allow the passage of electricity? Easy. Why does solid lead bromide not allow the passage of electricity? It does not have free and mobile electrons. Good job. Good job, Atika. Oh, Ajwa, sorry. Yes, Ajwa, you're doing a good job. Yes, Maruj. Yes, the ions are not free to move in the solid, so they cannot move to the electrons. Yes, no free ions. Yes, mobile and charged particles. Mobile and charged particles, remember, for conduction. What color is the vapor seen at the positive electrode? Brown. Brown vapors? Is the color brown? Huh? Are you sure? Okay, so, okay, brown gas. Yeah, okay, orange brown vapors or gas. Yes, okay, good job. Then give one reason why this electrolysis should be carried out in a fume cupboard. When do we use a fume cupboard? When do we use a fume cupboard? Yes, Ajwa, good job. Ajwa, you are doing preparation. I can see that. Ibrahim, lead is a solid, so it will be deposited on the cathode, and so it won't be in the form of vapors. Fume cupboard, as the name suggests, it's a cupboard that traps fumes. You know, fumes are like vapors in the air, droplets sort of. So the cupboard does not allow the fumes, the poisonous fumes, to be spread in the air that can be inhaled by people, right? So that cupboard keeps the fumes within itself so that, you know, the people can stay safe, right? Toxic, bromine is toxic. Okay, let's move on. It's because of bromine, okay, not due to lead. Fume cupboard. What is the alternative name for the negative electrode? Oh, yes, cathode. You know, sometimes they give these questions to just give away the numbers. You know, do you guys know that when I was a student, we wouldn't get such easy peasy questions like these. What is the alternative name for the negative electrode? This is just, they wanted to have another part to this question. Okay. This we won't do. This is about copper plating. 4.13. In the electrolysis of molten lead to bromide, the reaction occurring at the negative electrode was, which is cathode, lead ions plus 2 electrons giving lead solid. Write the equation for the reaction taking place at the positive electrode. Easy. Okay, I want you guys to do this. No need to laugh at me, Ibrahim. Exam is a nightmare. You haven't seen our exams. Okay. Okay. Tell me, Anode, who will write the equation to bromide? Give us bromine plus. Wonderful, Maruj. Bravo. Clap. Clap emoji. Where is it? I can't find it. Okay. I can't find it. I'll waste all the time. Leave it. Okay. Move on. Next question. Next part. Why is the reaction taking place at the negative electrode viewed as a reduction reaction? Chalo ji. Yeah, because at negative electrode, the cations are gaining electrons, and gain of electron is reduction. So easy. Now, 4.14. The tables list the results of the electrolysis of a number of aqueous solutions using inert electrodes. Use the information in the first table to complete the second table. The solutions were electrolyzed under exactly the same conditions as the ones above. Okay. What are these? Copper sulfate. So, okay. Sodium sulfate, and then this. Okay. Gas given off at the anode. Sodium nitrate. Gas given off at the anode. Solution. So what are the ions here? What are the ions here? Sodium nitrate, sodium and hydrogen. Of course, sodium will never be released. So it is hydrogen here. This is hydrogen. This is easy. I'm just writing H2. Okay. And then this blank, silver sulfate. Sulfate will always stay in the solution. Remember, sulfates, carbonates, nitrates. I will give you a reactivity series, okay? I'll send in the group. Sulfates, carbonates, nitrates will always stay in the solution. Okay, Yusra, you want me to do this in detail? Then of course, oxygen will be released, and then here you will have, okay, let me do this in detail. Okay, because Yusra is asking, she's not understanding. Okay. We are out of time, but it's okay. Those of you who are in a hurry can leave. I'm just solving this question and then I'm done. Okay, so I have silver sulfate, okay? Silver, and this is aqueous. Is it aqueous? Silver sulfate. All the sulfates are soluble except for barium, calcium, and lead. So silver should be soluble. Yes, okay, so it is soluble. Okay, and then silver sulfate solution is water. So giving me, so what are the cations? From water, I have hydrogen ion. From silver sulfate, I have silver. Here, I have sulfate from here. And then from here, I have hydroxide. I know this is never going to be given, so this will give me oxygen. Silver and hydrogen. Silver is below hydrogen in the reactivity series. Right, silver is below hydrogen. So here hydrogen got its chance. And hydrogen says all the time, sodium and all these metals keep pushing me, no way. This time silver, you go and get sacrificed. So silver will get sacrificed here. Silver will be discharged. Okay, so we have silver here. Now what is left behind? So substance left in solution at the end of electrolysis. So hydroxide is gone. Silver is gone. Sulfuric acid. Sulfuric acid is left behind. So you will write sulfuric acid. Yusra, are you with me? I'm not making the electrolytic cell and showing you the whole thing. I have just written down the ions and, you know, the competition between them. Hydroxide will be released, so oxygen is released. Silver, because silver is less reactive than hydrogen in the reactivity series, if you look. And so silver will be discharged, hydrogen will not. Yes, I will share the reactivity series, okay? Because I can only show you one thing at a time. I wish I could show you the reactivity series. It is written somewhere else. Okay, so hydrogen will be released. Okay, so oxygen, they asked the gas given off at the anode, so that is oxygen. They did not ask gas given off or metal deposited at the cathode. So this time it is metal, and this is sulfuric acid. Okay, here sodium nitrate. Sodium nitrate. What do I have in sodium nitrate? Easy. Now again the bossy sodium came. So hydrogen will be released at the cathode. Hydrogen will be released at the cathode. No. So yeah, at the cathode. Yes. And then at the anode, we have nitrate. Nitrates, by the way, also stay in solution. Oxygen will be released. Here, this is wrong. You should write oxygen here. Oxygen hona chahiye. Yeah, hydrogen, and then what is left behind? Hydrogen is gone. Sorry, hydrogen carrying. Oxygen is gone, hydroxide is gone, hydrogen is gone, sodium nitrate is left behind. Sodium nitrate is left behind. Sodium nitrate is left behind. Okay, that's it. Any questions? Please ask me. Yes, Ajwa, reactivity series is on page 216 and 218 of the book. Okay, whenever you learn or read, you know, all these topics that you have been doing since grade 6, at least them, you know, the story is continuing. So if you forget those, how will you continue the story? Okay, the story is continuing. So that's that. Any question? Ask me. Okay. Okay, is there any question?
Ma'am, were you tired today?
Yes, Arham?
You were tired today.
You were tired today?
Yeah, because you kept on answering the some of the questions wrong again and again.
Oh, I'm so sorry. Yeah, at least I mean, why am I listening these devices and, you know, other unnecessary sound from the background? I'm sorry about that, Arham. Yes, because I had to write a lot of half reactions and overall reactions. And, you know, when you're doing it live in front of so many people. So yeah, I made mistakes. Sorry about that. But I hope you understood. Did you understand, Arham? Did you understand? Yes. Okay. I'm ending the meeting. Jazakallahu khairan. And tomorrow we will continue with this. Okay, we will inshallah finish it off tomorrow. We will do electroplating and purification of copper. And if time allows, we'll do end of chapter questions. But I will give one whole class to the questions. One whole class only for questions. End of chapter questions, and we will do redox reactions. Okay, and how to calculate oxidation states. Okay, I'm ending the meeting. Assalamu alaikum wa rahmatullahi wa barakatuhu.
We'll see you soon.